In this example, again, we're going to revisit the RL step change example where we're going to use the general first order step input response model to come up with the solution for this system. Again, we're looking for the current and how the current is going to change through this inductive element before the switch is before the switch right here closes. The current is going to be flowing through a total of 6 ohms of resistance, and after this switch is closed, the current will bypass this 5 ohm resistor, and we will be flowing through only that 1 ohm resistor and then through the inductive element. So again, what we need to do is we need to establish the 3 important parameters for the first order system. We need our initial condition, our steady state value, and the time constant. So the circuit that we're interested in analyzing is what happens after this switch closes. So I'm going to look at 2 cases here because we're going to need both of these cases to establish the initial conditions as well as the steady state conditions. So before the switch closes, the circuit that we have on hand is the 12-volt supply is going to be going through, is going to be connected to the inductor through a total of, this is 1 and this is 5, through a total of 6 ohms of resistance. Okay, and then after the switch closes, after R2 closes, this resistor is going to be shorted, so all of the current is going to bypass through that switch, and the circuit that we're interested in looks like a 12-volt supply connected to a 1 ohm resistor in series with the inductive element. Okay, so the circuit that we're interested in analyzing right here is the one right after that switch closes, and we're looking for how the current changes through this circuit. All right, so to come up with the time constant, we need to establish our differential equation model. And this is R1, R2. Over here is R1 plus R2, and L1. Oops, sorry. This is L1 right here. Sorry about that. Okay, so again, since we're looking for a current, we're going to use Kirchhoff's Voltage Law. And Kirchhoff's Voltage Law tells us that the input voltage needs to be dissipated or dropped across, the potential has to be dropped across all of the other elements of the circuit. So that tells us that the input voltage has to be balanced by the losses across the resistor, which is going to be R1, and the inductor. And now using our current to voltage relationships, we can substitute in the current to voltage relationship for the resistor and for the inductor. For the resistor, it's going to be that current times the R1 resistance value. And for the inductor, we know that the voltage to current relationship for the inductor is given by L times the rate of change of the current through the inductive element. That has to be equal to Vn. And then we'll put this into standard differential equation form by dividing by R1 and rearranging. And we'll wind up with L1 over R1 times the first derivative of current with respect to time, plus the current has to be equal to Vn over R. So now we have our first order non-homogeneous or first order step input model for this circuit. Again, the term in front of the first order derivative gives us the time constant. Alright, so now we need to turn our attention to finding the initial condition and the final steady state value of the current. Okay, so to find the initial condition, right before, we're going to look at what's happening in the circuit right before the switch closes. So right before the switch closes, the current, we're going to assume that the inductor has been operating in the steady state for a long period of time. So that means the magnetic field is fully established. And in this case, the inductor is going to act like a wire. So the only elements that exist in the circuit is the combination of R1 and R2. Therefore, all 12 volts has to be dropped across that total of 6 ohms, and that tells us that the current through those resistive elements and through the inductor as well, which is now acting like a wire, has to be dictated by the resistance and the voltage. So the current in this case is going to be V over R, So right before that switch closes, we're going to have 2 amps of current flowing through the circuit. Because right after we flip that switch, because of the properties of the inductor, we know that the current through an inductor cannot change instantly. So right after we flip that switch, there's also going to have to be 2 amps of current flowing through the circuit. So right after the switch changes position, we know that the current the magnetic field is still established and can't change quickly or instantaneously. So the current through the inductor gives our initial condition at time 0 to be 2 amps. All right, so initially 2 amps of current will be flowing through this inductor. And now we repeat the similar analysis. What happens as time approaches infinity? All right, so as now we have removed the 5 ohm resistor from the circuit. This one is now gone, so we only have 1 ohm of resistance after the switch is closed. And after that switch has been closed for a long period of time, the magnetic field of this inductor becomes fully established, and it again begins to act like a wire. All right, in that case, when this acts like a wire, the current is dictated only by the resistance and the potential that's applied to the circuit. So since we have 1 ohm of resistance now, as time approaches infinity, the current is going to go to V over R, or 12 amps. All right, so we're going to start at 2 amps of current right after that switch closes, and we're going to approach 12 amps. All right, so now that we know the time constant, the initial value, and the final steady state value of the system, we can use our general model to establish the solution, or how the current is going to change as a function of time. The general step inputs result tells us that if we know the initial condition, we take the initial condition, subtract the final steady state value, multiply by e to the negative t over tau, and add in our steady state value, which in this case, since we know all of these, it's going to be 2 amps minus the steady state value of 12 amps times e to the negative t over tau plus 12 amps of current, which is going to give us negative 10 amps e to the negative t over tau plus 12 amps. And of course, if we substitute in our value of tau here, that will give us negative 10 amps times e to the negative t times R1 over L1 plus 12. And of course, that has units of amps associated with it. So this will describe how the current through that inductor is going to change as a function of time. So when time is equal to 0, this entire term, this exponential term, goes to 1. So we'll have 12 minus 10, which gives us our initial condition of 2 amps, as we have modeled up here. And as time approaches infinity, this value, as the exponential term, is going to get smaller and smaller. So this 10, this subtracting 10 is going to get smaller. So this entire term starts becoming less and less and approaches 0. So eventually, as time goes towards infinity and the switch has been closed for a long period of time, we're going to approach 12 amps of current through the inductor. And that's exactly what we have come up with right here. If we plug in the values of R1 and R2 and Vn, we should get the same results. And you see that we start at 2 amps and we approach 12 amps, and these different lines represent the different values of the inductor. All right, as we increase the size of the inductor, since our time constant is L over R in this case, as we increase the value of the inductor, the time constant gets longer, and the time that it takes to approach that steady state value from the initial value of 2 amps is a longer period of time.